Good morning, good afternoon, and good evening, everyone. Welcome to our tutorial. I'm Zhentong Yan, a doctoral student from the University of Helsinki. This tutorial is a joint work with Huawei. In this tutorial, we will talk about workload forecasting and performance prediction in database. Those are very important if you want to make wise decisions for your DBMS. This is the outline for the tutorial. Now, the modern database systems are becoming more and more complex, which brings a lot of challenges in management. First, we may have a large number of instances. For example, a cloud database may have millions of instances. So it is pretty difficult to provide specialized optimization for each instance. Second, the tuning tasks become extremely complex due to the large number of knobs. And finally, workload may dynamically change over time on each instance, like with different workload types and different arrival rate. 73 dBA sync performance tuning occupies the most of the time. And 75 of IT management budgets are spent on the database management. An ideal solution for those challenges is the autonomous or self-driving database, because the autonomous database can find better configurations than the DBAs, and they can reduce administration costs. And finally, users can focus more on the higher value business activities instead of the boring tuning tasks. The first self-driving database system in academia was proposed by CMU Database Group in 2017. The system was called as Pelton. Several months later, Oracle released the 18-version database and called it as an autonomous database. The self-driving concept by CMU is that a DBMS that can deploy, configure, and tune itself automatically without any human intervention. So the self-driving database should select the actions to improve the performance. And it can choose when to apply an action and learn from those actions to refine the future decision-making process. The concept in Oracle is similar. It says to use machine learning to automate the database tuning, security, backups, and the other routine management tasks without human intervention. So this figure shows the workflow and the architecture of a self-driving database called Pelton. The middle part is about the workload modeling and the workload forecasting, which contains two components. First is the workload for classification, and the second is the workload forecasting. Pelton uses machine learning models such as recurrent neural networks to predict the arrival rate of queries for each workload cluster. In the control framework part, it will continuously monitor the system performance and select the optimization actions to improve the application's performance based on the forecasted arrival rate of the workload. The Pelton project has been ended, but the same group proposed a new system called Noise Page in 2021. We can say that the architecture consists of three components. First is the workload forecasting. Second is the behavior modeling, and the last one is the action planning. So forecasting allows the DBMS to prepare itself for the future workloads, much like a self-driving car predicts the road conditions up ahead using a radar or cameras. So based on this forecastings, the action planning component will select the best actions, such as the creating index or changing the knobs to improve the system performance. The behavior of an autonomous database can be described with this formula, which means the performance of a DBMS is both decided by the system configuration and the workload it has to process. And many optimization problems are based on this formula. For example, giving an estimate workload, we want to find the best configuration to maximize the system performance. Or giving specified goals for the performance and the workload properties, find the lowest cost configuration that can satisfy the performance goals. So in autonomous database, we must and should utilize the workload information to adjust the configurations for gaining the optimal performance. However, there are some challenges. First, there is no one-size-fits-all configuration that can work for all workloads. So we need to understand the application's workload at first, and then all these configuration actions should be based on the workload information. And the second challenge is that we need to make configuration in a predictive manner rather than a reactive manner. This is because it is too late to reconfigure the database after the workload changes, because this would place additional burden on the already overloaded system. So it is far more reasonable to reconfigure your database before the workload changes. However, this kind of predictive configurations requires knowledge about the future workload. Thus, in this tutorial, we will focus on how to acquire these knowledges about future workloads. For example, we need to know when the workload will change in the future, and this can be achieved by workload shift detection. We also want to know how many workloads will arrive in the future in a period of time, and this is called as a arrival rate estimation problem. Besides the time information and the volume information, sometimes we want to know more details about the workloads, such as what will be the next query or transaction that a user will execute. Those forecasted workload information can help us to configure the database, such as creating index or assigning resources to optimize the performance. So after the database receiving the set of queries, it would be helpful if we know the execution time or the resource demand of each query. This is usually called as a performance prediction problem, which can be used in many tasks, including the query scheduling, admission control, and the system sizing. So in the third part of this tutorial, we'll show you how to utilize the estimated execution time and the memory demand to optimize the performance of Redshift, which is a data warehouse in Amazon. So this is a reference for the first part. In the second part, we will go into the details of workload forecasting and the performance prediction. At the beginning, the first question we need to consider is, what is a database workload? So it is difficult to give a precise definition because it depends on what you are trying to achieve. If you regard the workload as the total requests made by the users or the applications, for instance, the SQL statements that have been submitted to the database, then you are using the purest definition of workload. But if you focus more on the system statistics, like the CPU usage, memory usage, and the elapsed time. You're actually using a more liberal definition. So the definition is really depending on your target. Let's go back to these topics in this tutorial. We'll notice that the first 5 workload features are based on the purist definition, and the last one is based on the liberal definition. There are some demands for a good forecasting and prediction method. It should have good accuracy, low cost, and can handle different workload types such as OTP, OLAP, and even mixed types. We also hope it can handle multiple workload patterns, including cyclic spike patterns. And it should also be robust to a noisy workloads and the workload fluctuations. Finally, we hope the method can adapt to all kinds of changes. So this means you don't need to rebuild your models after the date or the hardware changes. This table gives a summary of the methods that can be used for workload forecasting and performance prediction. Among those methods, we can say that machine learning models can be used for almost all the tasks. And among those methods, the time series analysis, analytical modeling, and stochastic modeling are called as the white box approaches. The others, including experimental driving, machine learning, and reinforcement learning, are usually called as black box approaches. First, let's talk about workload shift. So this paper uses a model called Ngram to detect the workload shift. So first, what is a workload shift? A significant change in the workload that could require reconfiguration is called the workload shift. So the idea in this paper is to model the workload as a Markov chain and detect the workload shift using Ngram models. This figure shows a two-staged workload analysis framework. In the first stage, the workload shift detection component will continuously monitor the information about the current workload. If a significant change in the CPU or the memory usage is detected, then the second reconfiguration analysis component will be started to reconfigure the database, for example, to change the physical design or to change the configuration parameters. So the key idea is in this paper is to model the workload as Markov chain. And this figure shows an example of the workload modeling. In this figure, each node represents a statement type, such as a query, inset, or an update. And each statement type will be mapped into a Markov state. The probability of the forthcoming events depends only on the current state. And the transitions between states are modeled as the attribute ARGs. Finally, we can use the Ngram models to detect the workload shift based on those Markov model. This paper in 2010 used different methods to predict the periodic workload changes. So this figure shows 3 different workload periodicity. First, the regular workloads appears at specific time steps, such as every morning from 6 a.m. to 10 a.m. And the interval workload appears in regular intervals, for instance, every 10 hours. And the pattern workload follows a setting activation pattern. For example, after 2 hours, 4 hours, and another 2 hours and 4 hours. So in this paper, the workload is not modeled as a Markov chain. Instead, it will be modeled as a time series or discrete signal. And then the discrete Fourier transform and the interval analysis can be used to detect the periodicities in the workload. This figure shows the model interval analysis decisions, the model interval analysis and the DFT algorithms. We can say that the model interval analysis detection is always more efficient than the DFT approaches. Next, let's talk about the arrival rate. So the workload shift does not provide any volume information. It only provides when the workload will changes, right? So the target of this paper is to predict the arrival rate of queries in the future based on the historical data. For example, how many queries will arrive per minute or per hour. So the framework in this paper is called QB5000. It can provide multiple prediction horizons with different time intervals. Here, the prediction horizon specify how far into the future a model can predict. And the prediction interval indicates the time granularity at which the model can predict. This concept is very similar with the sampling rate in signal processing. In real applications, there are many different arrival rate patterns. So this may be challenges for the arrival rate estimation. So the first figure shows the number of queries executed per minute by a box track application. So we can say it is a typically cyclic pattern because the DBMS execute more queries in the daytime, especially in the rush hours, than in the night. The second figure shows a different pattern. That's the queries will grow slowly at the start, but then it will increase significantly at a specific time. For example, before the deadline for admission in a university. This is a workload pattern called growth and spikes. And the last figure shows a workload evolution pattern. We can say that there is a large shift in the workload after the organization released a new feature in the applications. So the challenge here is to handle all of these workload patterns. This figure shows the workflow of QB5000. After receiving the SQL statement from the target DBMS, the processor will first convert the raw queries into generic templates by extracting some constant parameters out from the SQL strings. And it will then record the arrival rate history for each template. Then in the second part, the cluster will perform compression of the workload using a clustering techniques to group the template based on the arrival rate patterns. So in this step, we can use a lot of query features, like the physical feature and the logical feature of the query. But these two features are dependent on the database configuration and hardware, which means you need to rebuild your models after the configuration or the hardware changes. So we will use the arrival rate feature and not use this tool. And the algorithm in this part is called the DB scan, which will be used to do the clustering. Finally, the forecaster will select those templates cluster with the highest query volumes, and then use them to train forecasting models such as linear regression, kernel regression, and recurrent neural networks. These models will be used to predict how many queries will be executed in each template cluster in the future. In this workflow, we can say that pre-processor and the cluster steps can significantly reduce the computation and the storage overhead. So this picture shows the prediction result for cyclic patterns with different prediction horizons. We can say that both the predicted patterns of the error rate can mimic the actual patterns. This means it has accurate prediction performance. And the 1 hour horizon prediction is more accurate than the 1 week horizon, right? And for the spike patterns, we can say that the ensemble and the ensemble learning method with its two base models, the linear regression and the recurrent neural networks, are unable to predict the spikes in the workload. The kernel regression is the only method that can predict the spikes because its prediction is based on the distance between the test points and the training data. This means the influence of each training data will decrease with its distance from the text point. So the conclusion is that maybe a hybrid model that combines the ensemble and the kernel regression is the best choice for error rate forecasting. Next, we will talk about pStore, which is an elastic system proposed by MIT in 2018. So the motivation is that for many OLTP applications, the maximum load is several orders larger than the minimum load. So you can say this figure shows the workload of an online retail company over 3 days. The vertical axis shows the request per minute, and the horizontal axis is the time. We can say that the peak load in the daytime is about 10 times larger than the minimum load at night. So in order to handle the peak load, those systems are often configured with a fixed and sufficient machines, which would be a waste of resources. For example, like this, we will provide a fixed number of servers to handle the peak load. So, but we found that the workload patterns is cyclic and predictable. So we can reconfigure the database before the workload changes. In this way, we can reduce the average number of servers in the OLTP application. So the key idea is to use a predictive model to elastically reconfigure the database before the workload spike occurs. So in order to achieve that, a time series models is used to predict the future workloads, and the dynamic programming algorithms is used to determine when and how to reconfigure the database, giving the prediction of the future workload. So the predictive problem in this paper is to minimize the cost C over T time intervals. Here, St is the number of servers in a database cluster at time point T. So in order to minimize the cost, the system should make the capacity to handle the queries as close as possible to the demand. And the capacity should be always larger than the demand. This figure shows the ideal case. In this case, the capacity curve would exactly mirror the demand curve with a smaller buffer. However, in actual, we can only have a discrete number of servers, so the capacity curves will look like a step function. And if your systems works in a reactive manner rather than a predictive manner, the capacity curve may become like this. So this means the capacity is smaller than the demand in this period, right? And this would degrade the performance of your database system. So the right figure shows an example of the algorithms from a high level. The target here is to find a series of moves start from this time point with 2 machines and end at this time point with 4 machines. So during this period of time, the algorithm should guarantee that the capacity is minimized, and the capacity is always larger than the demand. Here, a move means a reconfiguration action going from a machine number, for example, from 2 to another machine number like 3. So pstore uses a time series analysis method called sparse periodic autoregression, short for SPAR, to predict the future workload based on the historical data. SPAR is a kind of autoregression prediction models, which are able to capture the time-dependent correlations in the data. So this equation shows how to model the workload at time point t plus tau based on the periodic signal and the offset between the load in the recent past. So here, n is the number of the previous periods, and m is the number of the recent workload measurements. AK and BJ are the parameters of the models, and the tau is the forecasting period. It indicates how long in the future we plan to predict the workload. The SPAR can provide a good fit for the workload because the AR component is able to capture the autocorrelations in the workload. This is based on the assumption that the values are highly correlated with each other. And the SP component can capture the longer time periods, such as a weekly or monthly trend. So these two figures shows a prediction result of a SPR method. The first one shows the predictions for a 24-hour period with a forecasting window of 60 minutes. We can say that it has good prediction performance. The predict load is almost the same as the actual load. And the second one shows the mean relative error with different forecasting window. We can find that the prediction accuracy will decrease if we use a larger forecasting window. Finally, let's see how pstore can be used to optimize the query performance and reduce the number of servers. So here, the red line is the machines in the cluster, and the green line shows the average average latency after the reconfiguration. And the black line shows the static configuration. So the first figure shows that when running with 10 machines, the average latency is very low, and with only 2 small spikes. This is because we provide enough machines to handle the peak load. If we reduce the number of machines, then the number of the high latency transactions will increase in those areas. So the third figure shows the result of eStore, which works in a reactive manner. So the eStore can correctly react to the load changes and reconfigure the system to meet the demand. However, it has higher latency when the load increases every time. You can see the red line shows the spikes every time the workload increase. And the last figure shows the result of pStore. Compared with the eStore, we can see fewer latency spikes, it is almost the same as the first figure. This is because pStore can reconfigure the system before the workload increase, and the eStore can only react to the workload changes. In the following slides, we'll talk about how to predict the next query that a user will execute. So the first paper is called the promise. This means predicting the user behavior in multidimensional information system environments. So the idea is to estimate the next query that an application will execute using Markov models based on the analysis of the user's behaviors. So this figure shows the example. In this figure, each OLAP query will be modeled as a state in the Markov model. And transition from the state S1 to S2 is labeled with the probability. This means the query Q1 is followed by another query Q2. This paper in 2009 used both the Markov process and a peer tree network to estimate the next transaction that a user will execute. So the key idea is that we first use the Markov process to model the relationships between transactions, and then we will use the Petri net to model the OTP systems whose transaction has no relationships. So similarly, here, each transaction is an individual state in the first-order Markov models. And in this example, we can say that we have 5 transactions corresponding to 5 states. They are browse, search, add to cart, select, and pay. And the transaction probabilities are assigned among those states. For example, the probability transit from browse to select is 0.2. So a paper in 2021 utilized the machine learning and the reinforcement learning to predict the next query. The motivation is that prediction of the next query from the user can help in the query processing and increase the interactivity. So the problem definition is giving a sequence of SQL query, Q1, Q2, and we want to predict the future query qi plus 1 at the next time step I plus 1. This figure shows the end-to-end functionality of the system. So given an SQL query qi issued at time step I, we will drive a fragment embedding for the qi as a big factor. Then the embedding vector will be fed into the predictors to predict the fragments in the next query qi plus 1. Simultaneously, qi is executed and its results are returned to the querying application. And also the predicted embeddings of qi plus 1 will also be returned. So in this paper, the recurrent neural networks and the exact Q-learning will be used as the predictors. And as schema, our SQL fragment embedding mechanism based on one hot encoding is used to encode the queries. So first, recurrent neural networks is a kind of powerful temporary predictors, which is very suitable for the tasks of predicting next query. So in the training phase, the query embeddings at the time step ti will be input to the RNN model, and the RNN model include a batch normalization layer, and it will use a dropout regularization mechanism to stop the training process. At the test phase, we will use the same model, but at the output, we'll pick the top k next query candidate from the historical pool as a result. Different from the recurrent neural networks, we can also use reinforcement learning, such as exact Q-learning, to predict the next query. Q-learning use the Markov decision process to capture the temporal dependencies among various states. So this is very similar to the previous papers that utilize Markov chain to model the behaviors of the queries. But in this paper, we will use a more advanced reinforcement learning framework to solve this problem. So in this framework, the agent is a predictor that is used to link the Q tables and predict the next query. In the Q table, rows are all possible states, and the columns are all possible actions. And each cell in the Q table is a Q value, which is a long-term reward that the agent can get by executing a query after another query. All the cells in the Q table will be initialized to 0. Then each cell will be updated through the training process. So, and the right figure shows how to update the Q value based on the Bellman update equation. So the state action space in this framework is the embeddings of the training queries. So note that both the state and the actions in the Q table is a distinct training query. For example, query 1, query 2, and query n. If you execute a query, you have taken action, and the state will transit from the current time step to the next time step. At each state, the agent can take an action to transit to another state and get an instant reward. These instant rewards will be accumulated and updated in the Q table. So the goal of the Q-learning is to find a series of actions to maximize the long-term reward. In this paper, the reward is a combination of the Boolean and the numeric reward functions. Okay, so until now, we have talked about the workload forecasting, including the workload shift detection, arrival rate forecasting, and the next query prediction. Next, we will talk about the performance prediction, including execution time and the resource usage prediction. So the query performance prediction problem is called as a QPP problem. For example, we want to estimate how long queries will run. This is called the execution time prediction. It is perhaps the most important metrics for a query. And other problems like how much CPU times they will need and how many disk IOs they will incur. The QPP problem is very important because they can be used for a lot of tasks. For example, the workload management, like the admission control, that is, should we run this query or not? And the query scheduling, and like when should we run this query? And the QPP can also be used for system sizing and resource allocation. For example, how many CPUs, disks, and buffer pools is needed to run. And it can also be used in the physical design tasks, like what kind of index is needed. So in the case study part, we will introduce Amazon's Redshift, which utilize the machine learning method to estimate the execution time and the memory usage of each query for the tasks of query scheduling. So this is outline for the QPP problem. We can say between the 2007 and 2011, the machine learning models are used to the QPP problems, but those methods use different features, and they can be used for different kind of workloads. For example, the single workload and the concurrent workloads. So in 2011, an experimental driven method is proposed, and this method has been adopted by IBM DB2. And after that, some analytic modeling that use calibrated cost models are proposed to estimate the query execution time. And in recent years, the deep learning models like the tree structured deep neural networks and the graph embedding methods like the graph neural networks are proposed to solve the QPP problem. So a paper in 2008 is called a PQR tree. It is a method used to predict the query runtime. So there are some key insights in this paper. The first one is it is unnecessary to estimate the precise value for execution time. So it is sufficient to produce an estimate in the form of time ranges. And the second insight is we can use the query plan vector, the optimizer cost, and the load vector as the input to estimate the query runtime. So this figure shows the architecture of the workload management system. Once the query optimizer receives a query, it will output the query plan and the cost as the input to the PQR model. In addition, a load monitor will extract the a load feature vector and the execution cost, which are also as the input for the PQR model. Then the PQR model will estimate the execution time of the query and the current input. This estimate is passed on to the workload manager, which is responsible for scheduling the queries. Notice that all the information about the query execution will be fed back to the workload manager, which can be used to adopt the appropriate actions to modify the problems. So the problem of the time range estimation is that instead of predicting a precise value, we will predict a time range for each query Q with the formula of that. In this formula, TQ is the query execution time, and the TA and TB are the bounds for the some predictable intervals. And a PQR tree is a binary tree like that, and each node is an associated two-class classifier. And each node contains some examples for the training. Each node will have an associated query C and correspond to a time ranges. In this example, we can say that the classifier in the root node is a classification tree with a time range from 1 second to 2,690 seconds. The root node has two children that divides its range into two smaller ranges. And we can say the associated accuracy of this classifier is 93.5%. So the rest of the nodes can be understood similarly. This means we will divide the smaller time ranges into a smaller time ranges, and finally, we will get 5 leaves in this PQR tree, and each leaf is associated with a specific time ranges. For example, the first leaf shows a time range from 1 to 13 seconds. The PQR tree has some drawbacks. For example, since we don't know the time ranges in advance, so this means we have to fix the number of time ranges and this corresponding to the leaf node, the number of the leaves in the PQR tree. And this is a drawback of PQR tree. But the PQR tree also have some advantages based on this structure. For example, we can find different classifiers for different time ranges. And with the depth of these trees increases, the number of the classes increase. And as a result, smaller ranges of time intervals can be obtained. Different from the previous paper, which can only predict the execution time, this paper aims to predict the multiple performance metrics of the BI queries using some statistical machine learning approaches. So this figure shows workflow of this method. But giving a standard database system configuration, we want the vendor to use the training workloads runs to develop predictive models and tools. And those tools and models will then be distributed to the customer side of that based on this configuration. And those models will be used to predict the query performance. The goal of the approach is to predict multiple metrics such as the CPU usage, memory usage, disk usage, and the elapsed time. So the selection of machine learning models can have a big influence in the prediction performance. Thus, a key consideration when choosing machine learning models is to figure out whether it can find the multivariate correlations among the query properties and the query performance metrics. So after evaluating a number of machine learning models, the author found that KCCA has the best performance. So this figure shows the steps to build a predictive KCCA model. First, we need to create the feature vectors for all the points in the two datasets, query plan dataset and the statistic dataset. Then we will combine those vectors into a query feature matrix and a performance feature matrix. In this matrix, each row is corresponding to a same query. And similarly, in this row, each row is corresponding to the same query of the statistics. Next, KCCA will use a kernel function to compute the distance matrix between every pair of the query vectors and the performance vectors. So this paper conducts several experiments to evaluate the prediction performance. The first figure compares the prediction with the actual elapsed time with the predicted elapsed time for a range of queries. So the predictions we can say that the predictions were quite accurate, except some outliers, such as these two red cycles. One is caused by an underestimation record, and the other one is caused by a overestimation of the disk IOs. So in the second experiment, we can say that the predictions were not as accurate as the first experiment. This is because in the second experiment, we only use 90 queries for the training. And in the experiment 3, we use a two-step approaches using multiple models to conduct the prediction. We can say that the predictions are more accurate than experiment 1. And in the last experiment, we use different tables to train and test the models. This is an experiment to test the generalization ability for this machine learning model. And we can say that both the one-step and the two-step predictions shows poor performance, especially in the long-running queries errors. So this gives us some conclusion that more data in the training set is always better, and the few outliers can improve the performance. For example, if we can remove the outliers in this experiment, the prediction performance will be improved significantly. So the next paper in 2011 are different from the previous paper that use query and query plan features. This paper used an indicator called BAL to predict the query latency. So the problem here is giving a collection of concurrent queries. This means we will This means that this paper will consider the concurrent scenarios. And we want to predict when each query will finish its execution. So the key idea is to use indicators to quantify the performance impact on those concurrent queries. So the indicator here is called a BAL, buffer access latency. It is a robust and a good indicator for the query performance, even in the presence of the concurrency. So if we average BAL over the duration of the query, we can capture the interactions of the disk six and or the sequential rates, the operation system cache hits, and the buffer pool hits. So based on these good features, BAL is a good indicator for latency because it is averaged over many samples over the lifetime of a query. In order to predict the query latency, we need to train two models. The first one is called B2CB model, which will train to predict the BAL indicator. The second model is called B2L, which will take the BAL as the input and output the latency estimation. So in order to do that, we need to conduct a lot of experiments to average over many samples of each query class and record the BAL and the latency metrics for each query class. And in the prediction phase, we'll first use the B2CB model to predict the BAL indicator, and then use the B2L model to predict the latency for each concurrent query. So here is an example of how to predict the BAL of query A, which is being running with the query B and query C. So here TB, TA, TB, and TC are the averaged isolated BAL for each query. And the delta TAB, delta TAC shows are the changes in the BAL, which indicates when the query A is running with query B or running with query C. And finally, the average BAL for query A is a linear combination of those values. This means we'll not only consider the isolated BAL, but also consider the concurrent influence of those queries. This slide shows the prediction results of the BAL method. So the first figure shows the prediction results when using the B2CB model to predict the BAL indicator. We can say that there is some variance in the result of BAL. However, those variance will be reduced in the B2L model. In the right figure, we can say that each line is an individual B2L model for the prediction, and we can say that the regression model can achieve an average error of just 5%, and the variance in the B2CB model is being removed in the second model. This means the B2L model is robust to the prediction errors in the first model. So next, we will introduce a paper that uses the cost model to predict the execution time. So the idea is very simple and directly, right? Why we not use the cost models in the current optimizers to predict the execution time? However, this we cannot directly use those cost models. Let's say the example in PostgreSQL. So the cost model in PostgreSQL will use a combination of the I/O and the CPU cost that are weighted by some constant factors. For example, the CS and the CR is the I/O cost. This means the cost for read a page in a sequential manner or in a random manner. And the CT, CI, and CO means the CPU cost when we're processing a tuple or when we're increasing a index tuple. And finally, the cost CO is a linear combination of these Cs and Ns. And the Cs are some constant factors. Ns are the estimated cardinalities for each operator in the query plan. So this table shows the constant factors in the cost model of PostgreSQL. Those default values are meant to reflect the relative difference between the random access, sequential access, and the CPU costs. For example, processing a tuple in a CPU is almost 100 times cheaper than the sequential reading it from a page. Sorry, here I have an error. It should be CS, not CR. If we compare the CT with the CR, it would be 400 times cheaper, right? And those consistent factors are treated as the average over the entire mix of queries. So this means those constant factors may be not accurate for some specific queries. So this is because they are used to cover the most cases for the queries. And for the cardinality estimation, there are some assumptions like the uniformity, independence, and the principle of inclusion assumptions. Unfortunately, those assumptions are frequently wrong in the real-world datasets. We'll say later that those assumptions will cause the underestimation result for the cardinality. So an experimental paper in VLDB provided some good results for the cardinality and the cost estimation. So this paper evaluates five DBMS with a lot of queries using the GOB benchmark. And there are some key findings in this paper. First, all the cardinality estimators produce large errors. And the cost model has much less influence on query performance than the cardinality estimates. So this tells us it is better to improve the cardinality estimation rather than to improve the cost model. So this figure shows the results of the cardinality estimation in this paper. The horizontal axis is the number of joins. And the vertical axis shows how far away you are from the actual cardinalities. So the red line shows the perfect accurate estimation. Above this line is the overestimation, and below is the underestimation. We can say that all the 5 databases tend to produce underestimation result. If we add more tables in the join query, right? Why? This is because the assumptions that we discussed before, such as the uniformity and the independence assumption, those assumptions are wrong in the raw dataset. This figure shows the correlations between the cost and the runtime of queries in PostgreSQL. We can say that in these first three figures, that a poor cardinality estimate would lead to a large number of outliers and a very wide standard error, right? Instead, if we use the true cardinalities, the cost models will become a reliable predictor for the runtime. So the question here is how to obtain the true cardinality for different queries. This figure shows the naive scaling. That is, can we predict the execution time T by scaling the cost estimate C? You can say that if we use the naive scaling, it will generate a large error. So why naive scaling fails? Let's consider the cost model of PostgreSQL. We can say that this is because both the CS, which are the constant factors, and the NS, which are the cardinality estimations, both the two kind of values are not correct. So, to overcome the naive scaling, we have two solutions. The first solution is use machine learning models, and the second solution is to calibrate the constant factors and the cardinalities in the cost model. So these two figures show that the cost models will become much more effective after the calibration. You can say that the execution time is predicted more accurate by the calibration. So how can we calibrate the CS and NS? In this paper, the authors use the profiling queries to calibrate the constant factors first. Then the authors use the refined cardinality estimation method to calibrate the cardinalities, and calibrate the CS by running a family of profiling queries on the system first. Next, we calibrate the cardinalities by re-estimating the cardinalities using a sample-based approaches. This figure shows the evaluation results. The calibrated cost model is compared with the other three methods: naive scaling, SVM, under the REP tree. In this figure, ET means the estimation results with the true cardinalities. It is the baselines in this evaluation. And the EO means the estimation with the cardinalities by the optimizer without refinement. And the ES means the cardinal estimation results with the cardinalities calibrated by the sampling method. And the EOLR means the naive scaling. First, we can say that if we use the true cardinality to predict the execution time, we can get the best performance in both the uniform data and the skewed data. This is showed by the ET. And of course, the naive scaling, EO, LR shows the worst performance. And second, let's focus on the EO and the ES. So first, in the case of uniform data, the cost models with the properly trained CS already worked very well. This is showed in the EO. So the sampling method does not help much improving the prediction accuracy. You can say that the EO-ES are very close to each other in the uniform data. But in the skewed data, the sampling methods can be very helpful to improve the prediction accuracy. You can say that the prediction error of the EO is larger than the ES, which is the estimation of the sampling method. And finally, we can say that the performance of the machine learning-based approaches, ESVM and EREP, is not consistent. For example, for some queries, the prediction of the PC1 is better than the PC2. The PC means different machines, but in the skewed data, the PC1 will perform worse than the PC2. So there's some drawbacks of the machine learning models. So the next paper is called QBPNet. It is deep learning approaches. The key ideas in this paper is that the current approaches have some limitations. For example, both the traditional method and the BAL, that's the indicator-based method, cannot capture the complex interactions between the query operator and the input relations. So a solution is to use a plain structured neural networks, which can match the structure of the query plane. So this figure shows a plain structured neural network, which is very similar to the structures of the query plane. You can say that these two neural units called a scan unit is similar to these two operators, R1 and R2, and this join operator in the query plane is similar to this join unit, right? And the structures in this model consist of some operator level neural networks, and each neural network is called as a neural unit. And the query plane is modeled as a tree of those neural units. So at the operator level, a neural unit is a neural network, and each unit outputs both a latency and a data vector. Those two figures shows two examples of the neural unit corresponding to a scan operator and a join operator. So after we create the neural units, we can stack them to generate a tree structure model. And each operator, in order to get this neural network, we can first get the query plane, and each operator in the query plane will be replaced with the corresponding neural unit. For example, this figure shows a query plane of a simple join query, and we can replace this R1 and R2 with the scan unit, and replace this join operator with the join unit, and finally, by input those the features like the scan types and the predict and the optimizer cost, we can get the query latency as the output. So you can say that the leaf neural unit in this neural network corresponding to the leaf nodes of the query plan tree, and the internal neural unit is corresponding to the internal operator in the query plan. So the QBNet is compared with for method in the evaluation result in the evaluation section. So the first two methods are some traditional machine learning method like the support vector machine and the resource-based features. And the third one is the third one called TAM is actually the calibrated cost model that we discussed before. And the last one is a general gain in structure without a tree structure, which can match the structure of a query plan. And we can see from the two pictures that the QBNet performs the best on both the TPC-DS and the TPC-Edge benchmark. And it seems that the general gain performs the worst. So why? We'll give the reasons in later. So these 5 figures shows the error distributions for the TPC-DS benchmark. We can say that all of the tested techniques give unbiased estimation, and the QBNet achieves a tighter error distribution, which means it has a lower variance. And for the distribution of gain, we can say that it shows a multimodal error distribution. This is because the general deep neural networks will using a L2 loss functions, and those functions may be not well structured to the problem's domain. And if this problems happens, and it will generate a multimodal error distribution. So this is why we have a large error in the prediction. And the last paper about the execution time prediction is a recent paper using the graph embedding called the G-predictor. So the problem is that giving a query workload with multiple concurrent queries predict the execution time of each query. So the idea is to use a graph embedding neural network to encode the features and use a prediction network to predict the query performance. So in the graph embedding network, each node in the graph model is a node in the query plane, and each edge between two nodes denotes the correlations between them. I will give you an example in the next few slides. So this is the architecture of the G-predictor. The G-predictor architecture consists of three components. First is the workload to graph. It is responsible for extracting the workload features and collecting statistics from the database. It will output a graph, and the graph will be updated and compacted in the graph optimizer. And finally, the outputted graph will be fed into the performance predictor to predict the performance based on the embedded graph metrics. So first, let's talk about the graph modeling. The first step is vertex modeling. Here, in this example, we have 4 concurrent queries. These queries are from the GOB benchmarks. We can say that the first 2 queries are join queries, and the third one is a simple scan query, and the last one is update query. After we input the 4 query into the optimizer, we can get the query plan, and then we can extract the operators in the query plans as a vertex in the graph. We can say this query is corresponding to this 6 nodes, and this second query is corresponding to the 4 nodes. And the features in the vertex, including the operator type, the query predict, the sampling bitmap, and the estimated cost. So next, after getting the nodes, we need to create edges to connect those nodes, and this is called as edge modeling. In this stage, we need to compute 4 types of correlations as edges. For example, the parent-child edge, which are used to indicate the data dependencies between the operators. And other edge types include the data sharing, data conflict, and resource competition. Let's see some example of the edges. We can say that the first and the third query uses the same table called AKA name. So there will be a table sharing edge between wave 4 and wave 5. So this table sharing is a kind of the data sharing edges. Similarly, the V9 and the V10 have the same subquery. So there is an intermediate result sharing between these 2 nodes. And there is a data conflict edge from V11 to V5, because V5 may wait for the lock until V11 to finish the execution. So based on the graph, now we can, based on the constructed graph, now we can encode the vertices and the edges into feature vectors to generate the vertex matrix and the edge matrix. So in the vertex matrix, each row is a feature vector of a vertex. So for example, this row is a feature vector for the V3. And we can say this example that show how to encode the operator of cost of the V3. In this cell, we can say it is a number of the cost in about this node. And in the edge matrix, each cell in the matrix represents the relationships between 2 vertices. For example, this cell represents the relationships between V4 and V5. And this because there are some data sharing and the resource competitions relationships between these 2 nodes. So the values in this cell is the sum of these 2 parts. And after we get the vertex matrix and the edge matrix, we can use them to predict the query performance. And we need 2 steps to complete the prediction. First, we need to embed the graph features with the linked weights to get an embed matrix H3. So in this step, we will use a 3-layer graph neural networks, and there are some benefits of using the graph embedding network. First, it can effectively reduce the computation work by extracting the local structure instead of searching the whole graph. And the second, it can concurrently process the local graphs of all the vertices. So in the next step, we will use the embedded matrix H3 to predict the final query performance for the concurrent queries. So we will feed the embedded matrix into a 3-layer network to predict the query performance. Those performance including execution time, startup time, memory requirement, and the CPU utilization. So this page shows the performance comparison between the G-predictor with some previous methods, including the buffer access latency BAO method, the QPNet, and a tree LCM-based cost model. We can say that the G-predictor outperforms all the other methods in all cases. And the BAL seems to perform the worst. And there are two reasons for this. First, the BAL only uses the buffer access latency as the indicator. So this means this feature is is too simple for the concurrent queries. And the second, the BAL only uses a simple linear regression model, which cannot link the complex correlations between the BAL and the actual latency. Instead, the G-predictor will use complex graph neural networks and the graph embeddings to encode both the features and predict the performance. So we can say that the G-predictor performs the best. So some takeaways for execution time prediction. So first, the real-world workloads are both dynamic and concurrent. So when we design the method, we need to consider both the dynamic and the concurrent workloads. And second, for traditional machine learning models, the features used are very important. For example, the BAL indicator, the query level features, or the query plane level features. And those features can have a big impact on your performance. And for the deep learning models, the general deep neural networks and the decision trees cannot represent the link between the nodes in the query planes. And the tree structured deep neural networks is better than the general DNN and the general decision trees. Graph embeddings is maybe the state-of-the-art techniques for the QBP problem at present. Here's a reference for the second part. So in the next part, I will give you a case study to show how the performance prediction can be utilized to improve the performance of some real-world applications. So we will talk about the Redshift of Amazon. Redshift is a fast, fully managed and scalable data warehouse. It has many customers. So the Redshift automates the performance tuning by using machine learning algorithms in the recent years. For example, the workload manager, shorted for WLM, will automatically allocate the resources using the machine learning prediction models Based on these predictions, the workload manager can schedule short-running queries ahead of the longer-running queries. And there are some automation optimizations in the Redshift, but in this tutorial, we'll focus on the workload manager. So the workload manager is able to allocate resources for queries and schedules queries to execute. And it also can monitor the system performance. So this example shows the workload manager can load the concurrent query process into the Redshift cluster with some leader node and compute nodes. So before 2017, the workload manager is a menu version, which uses a fixed and concurrency and the fixed memory. In 2017, a short query acceleration version, shorted for SQA, is proposed. In this version, the queries less than 20 seconds are accelerated by some mechanisms like the express lane. And in the 2019, the concurrency scaling was proposed to handle the workload spikes by routing the queued queries to different clusters that are automatically provinced. In the same year, at the different stage, the auto workload manager was introduced to use machine learning models to predict the execution time and the memory. So the flexible memory will assigned, and the concurrency will be assigned to different queries. And the queries are assigned with different priorities to optimize the performance. So in the workload manager, the users can create different queues, like the ETL queue and the analytic queue. Each queue will be set with a fixed memory and the fixed concurrency number. For example, in the ETL queue, the memory is set as 82%, and the concurrency is 15, which means that we can run at most 15 queries at the same time in this ETL queue. Similarly, in the analytic queue, we can run at most 10 queries at the same time. So this is good enough for some simple and fixed workload. But if your workload changes over time, it will have some problems. For example, it is hard to set the optimal configuration, and you need to retain the configuration every time after the workload changes. Next, the idle queues can waste some resources in the cluster. For example, if there are no queries running in the ETL queue, the 82% memory will be wasted, right? And in addition, due to the fixed concurrency number, some short queries can be blocked by some longer running queries. So in order to speed up the performance, Redshift introduced a short query acceleration, shorted for SQA. So let's consider a business system. A 1-second query may wait in the waiting queue for 1 minute. So this is a very bad experience for the users. To solve this problem, SQA uses machine learning models to identify short queries, and then route this short query to a new created queue called the shorty query queue. So here is an example. Here we have two queues. First is the ETL queue, and the second is analytic queue. Both the queues are configured with fixed numbers in the memory and the concurrency. You can say that there are already 15 running queries in the ETL queue and 10 running queries in the analytic queue, but there are still some queries in behind. So Redshift will use the machine learning models to estimate the execution time of those waiting queries. For example, it will after the prediction, it will find that there are two short queries in the ETL queue, and there is one short queries in the analytic queue, and those three queries will be loaded into the short query queue for execution. So by doing that, the Redshift can improve the query performance and the throughput. The Redshift will train the prediction models on each cluster, so that the decisions are optimal for the workload in that cluster, and to have a better prediction quality and adapt to the workload changes. The underlying models are refreshed periodically. The Redshift uses linear regression and the decision trees to estimate the execution time of each queries. And the Redshift can time out when the prediction is not correct. This is because the machine learning models are not 100% accurate. For example, if a query whose runtime is 30 seconds, but we might predict as 10 seconds using the machine learning models, then we will regard it as a short running query and load it into the short query queue. And after 20 seconds, we found that the query is still not finished. And in that case, we will time out this query and send it back to the user queue. So it is works like a feedback loop. So in the next version about the workload manager is called the concurrency scaling. So we found that most of the clusters are very busy, only for 1 to 2 hours in a day. So instead of provisioning compute for peak loads or peak periods, the CS saves costs by allowing the customers to provide compute to satisfy the steady state needs and automatically scale as they need to handle the peak periods. For example, in order to handle the peak loads, we may need 10 computer nodes, but the steady state only need 4 nodes. And the CS will recommend the users to use just 4 nodes to save costs in the resources. And in order to handle the peak periods, it will automatically scale by creating a new clusters called the concurrency scaling cluster. So let's consider the previous example. Here, we still have some longer running queries, right? Because the short queries has been loaded into the short query queue, and in the ETL queue, analytic queue will still have some longer longer running queries. And in order to speed up the performance, we'll create a new cluster called the concurrency scaling cluster. And we will, and all these longer running examples will be loaded into the into these scaling clusters. So in this example, we can say we run the 100 running we run 100 queries in different clusters, and finally, the scaling cluster will send the results back to the main cluster. So the last version of the workload manager is called the auto workload manager. So it can automatically manage resources like the memory and the concurrency by applying machine learning algorithms. Then it can schedule shorter queries ahead of longer queries. In addition, the users can assign higher priorities to some important jobs, like the CEO jobs, to get more resources. And everything, so this figure shows the menu workload manager configuration, and this shows the auto workload manager configuration. In this auto configuration, everything is set as auto, right? The users only need to set the query priorities for different queue. For example, the ETL queue is set with the highest priority, so it can get more resources than the analytic queue, which is set with low priority. So to summary, the auto workload manager apply machine learning models to predict the execution time and the memory. So by doing this, it can improve the user experience by scheduling the short queries first. And it can manage memory and the system concurrency adaptively. And it also use a feedback mechanism to deal with the wrong prediction by the machine learning models that we discussed before. And now, if we add the priorities into this workload manager, then this allows the users to specify the priorities for different queries. So, for example, here, those queries are assigned with different priority. H means high priority, N means normal priority, and L means low priority. So this assigned with higher priority will be assigned with more resources. And the system will automatically assign priorities if the users do not set the priority. And this is based on the prediction of the machine learning models. So the prediction model in the Redshift is quite accurate. It can achieve over 97% accuracy for both the execution time and the memory prediction on the average. So this figure shows the experiment results on TPC-DS benchmark. We can say that with priority, the response time can be improved by almost 5 times compared with the result with no priority. And we also compare the menu workload manager with the auto workload manager in the TPC-H benchmarks. This is the settings for the experiment. We can say that all the configurations in the auto workload manager are set as auto. And we can say the that's the average elapsed time in this experiment. We can say that auto workload manager is always performs better than the manual workload manager. The lower is better. So some takeaways for this case study. So the Redshift utilize machine learning models to predict execution time and memory for queries. And it can adaptively manage the memory and the system concurrency. And it also can schedule short queries ahead of longer queries. So by combining those features together, the Redshift can improve the throughput, provide better user experience, and improve the system utilization. So in the next part, we'll talk something about the open challenges for the workload forecasting and the performance prediction. So the first challenge is how to realize the robust forecaster and the predictors for some noisy workloads. And the second challenge is that how to make the reasonable configuration to enhance the performance if we cannot get incorrect workload predictions. And the next challenge is about the training data, because we need a lot of training data in the deep learning models. So how to acquire or even generate some valid training data for the machine learning and deep learning approaches is also a challenge. And lastly, it's about the incremental training of the learning models in the production environment. This means we need to effectively retrain and update the models for new data of deploying them in the real world production environment, for example, in the cloud. So how to efficiently retrain this and update these models would be very valuable for some applications. So last is acknowledgement. We would like to thank all the organizers and attendees of DASFAA 2022. We would also like to thank all the authors of the reference papers. And we would also like to thank Dr. Chunbin Lin from Amazon for his contribution on making the slides about the Redshift Workload Manager. Thanks. So, okay. So I think this is all about our tutorial. Thank you for taking time to attend this tutorial. Next is the Q&A from the audience. Thank you.